So today I'll be speaking about AI for beginners and just giving you guys a general introduction um, to AI, just so that it's easy to understand. And if you have any questions, feel free to ask, but I would prefer to keep the Q&A for the end. So what is artificial intelligence? Usually when people hear the phrase, they think of Arnold Schwarzenegger or, the voice from Her. But this can't be further from the truth. Modern AI is very different from how it's portrayed in TV and cinema. And these examples from science fiction, they're more what is called artificial general intelligence. Whereas what is currently we use in day-to-day life is more artificial narrow intelligence. This is narrow intelligence is when narrow intelligence is artificial intelligence that is used to perform specific tasks that will normally require human intelligence, such as classification, decision making, speech recognition. It outperforms humans in a specific repetitive functions. But when it comes to performing outside of its field of what it's trained to do, it often falls quite short because it hasn't been trained to do that. You can't. Yeah, I'll get around to that later. Yeah, so it's used to work on specific problems that have very particular solutions. And this idea that Terminators and Skynet are going to come and, I don't know, some humanized robot that is able to talk to you, that is able to feel love and develop emotions for you, it's incredibly far away. I'm not sure that we'll even see it in our lifetimes, honestly. Because the general intelligence, it's more than giving. I don't know. It's hard to explain. It's when everything feeds onto itself to learn from different parts, from constantly picking up new information. Whereas at the stage we are now, sure, you could maybe make a reinforcement network that learns from its environment, but it's still very new technology and it's not going to go that far. Well, in our lifetimes. Yeah, so narrow intelligence, image, facial recognition software, email spam filters, media monitoring, which is, for social media, if people are saying dangerous content, if there's poor imagery, or if people are bullying each other, you're able to pick up on that. Self-driving cars, even, which sounds more than narrow, but in reality, it's only been trained to do that one specific thing, and all the data it's been given until that point is only for that. AlphaGo, even Siri. You think that people often think that Siri is, a very generalized artificial intelligence, but in reality, it's been taught to do a few specific tasks, and that's all it does. It's very effective at the tasks it's been trained to do, but it can't do much else. And it has no genuine intelligence or any self-awareness at all. So what is artificial intelligence? Well, John McCarthy, one of the godfathers of AI, defined it as the science and engineering of making intelligent machines, especially intelligent computer programs. It is related to the similar task of using computers to understand human intelligence, but AI does not have to confine itself to the methods that are biologically observable. And intelligence in this situation is the computational part of the ability to achieve goals in the world. As a human, we're making these basic computations all the time, whether we know it or not. From, I don't know, deciding what pasta to buy at the supermarket, or even when you're reading by skimming text and then predicting what the end of a sentence could be to save yourself some time. Artificial intelligence is expressing these mental computations we make, but in machine language, so that the software can even learn or it can problem solve on its own. And it's not anything that we're not doing in our day-to-day lives. But of course, if well trained, it's more efficient than we could ever be. Like, for example, I'm sure we've all used bathrooms that have had automatic soap dispensers, or even those taps with a little sensor that turn on when you're ready to wash your hands. I'd say they're both artificial intelligence. They're both mimicking intelligent behavior. By putting your hand in a particular place, you're asking the machines to work. It's receiving the request and it's responding accordingly. If there was someone in that bathroom and you ask them to, give you some soap, they will receive the request and they'll respond accordingly. But it's not as easy as writing out a script and, kicking back and automating your workflow. It's AI can recognize patterns, make predictions, and provide insights. But it's really only able to do that from the sheer amount of data that until now was out of reach. It's learning from examples. So if you're not able to provide those examples, then, it's not going to be able to pick up the clues. Yeah. We're very lucky that in this day and age, we're able to, we have such a large access to data. And there's even companies that have their whole business model is to provide other companies with these data solutions. You have online marketplaces where you can, virtually hire people to not make data, but to prepare data for you. So whatever you're trying to train the artificial intelligence to do, you're able to get exactly what you need. Whereas until now, it's been much more difficult. Well, until, this century, because in the 80s, we had the AI, well, not in the 80s. I think the AI winter finished in the 80s. It was around, 1974 to 1980 is where all investments stopped. And then from 1980, Japan reinvested in artificial intelligence, and then we started learning about this again. But now we're all online. Everything we do, everything, we say in social media, or, everyone's able to make a blog and share their opinion, and all of that is data that anyone can pick up and use to their advantage. But anyway, let's talk about some of the subsets of artificial intelligence, because, it's a bit broad. The main part that people actually think is the entirety of artificial intelligence is machine learning. And it's an artificial intelligence technique that uses statistical methods to enable machines to improve with experience. It's all about getting the AI to accomplish tasks without being given the specific instructions, about teaching machines how to learn. After being given a set of inputs, the machine will then pick up clues and, provide you with a solution, provide you with a prediction. But there are also two types of machine learning. There's supervised learning and unsupervised, which they're very different, and they're often used for different things. Supervised learning is machine learning with labeled training data to work with. This is referring to effective to mapping an input to an output based on example input-output pairs. So it's all dependent on the data you put in. There's a common misconception that I see it all the time on websites like Quora or Stack Overflow, where people are asking why their model's not working, why can't they make predictions, and they just don't have enough data. All the data's not labeled well enough. Whereas, yeah, so supervised learning, it's often used for image recognition, question and answer, sentiment analysis, speech recognition. It's also used to make image descriptions and language translation. But, with image recognition, it uses input images. I'm sure that people have seen the photo. It's kind of a meme online. It's like dog or cupcake, and they have a large amount of uh, data that they're trying to automate the labeling process of this to save themselves a lot of time. And what's happened is certain photos of brown dogs with dark brown colored eyes that look like cupcakes in these tiny photos. And to a human it's easy to mistake the two, but um, computer kind of works slightly differently. We're using number vectors. But anyway, sentiment analysis is give examples of text that is positive, examples of text that's negative, or kind of excited, or mm, yeah, or the such. And after giving it enough training data, it's able to, when it reads other text, it can make a prediction of like, hey, this text has a 0.8 80% chance of also being sad based on the data you've already given it. And then the unsupervised learning is the type of algorithm that learns patterns through untagged data. And it mainly builds representations through mimicry. So it takes all the inputs you give it, and it kind of tries to mimic them. Like imagine picture generators. I'm sure you've seen the websites, this person does not exist, and this horse does not exist, where it's been given a huge amount of images of faces, and it's able to generate using a general adversarial network, it's able to generate an image that looks human, but it doesn't actually belong to anyone. It has a bit of errors, like earrings are very poorly represented, and there's a bit of pixelation around the sides, but otherwise they're quite, if you don't look twice, you'll probably fall for it. You'll probably be convinced that it's an actual person. And I remember a few years ago, there was a big thing about people making fake profiles on LinkedIn using the photos from this website. And they would often message business executives and try to, I don't know, find key information, try to work as spies using these fake people's photos. It was very interesting. To also generate videos, which is kind of when I'm sure, I wish I had a video example, but people use videos, black and white videos, and they colorize them using neural networks, and it's all very interesting. Language modeling, which my colleagues Nikoloz and Makho will talk about after my presentation. Also, creative writing and speech synthesis, which is using the text you've been given, using start of a sentence, finishing it off, or even creating entire conversations that haven't ever happened, just through unlabeled data, just through mimicry. And then there's deep learning, which is a subset of machine learning. made of multi-layer neural networks. So it's still just predicting an output based on a set of inputs. But instead of using a simple machine learning system, it uses what's called a neural network with multiple hidden layers. It takes an input, it performs several rounds of math on its features, and then it predicts an output. The rules of machine learning still apply, but it works slightly differently. So this is a image of the top is a neuron, and it's called, and this is a, well, I guess it's neuron as well, but it's the machine learning version of a neuron. It's like a perceptron. So it takes in a set of inputs, and then it performs a function on them, which in turn gives you outputs. And these are often grouped together in a net using multiple layers in order to, they can feed forward, they can also they can back propagate, they can do many things. But it's taking the inputs, it's performing a function on it, getting passed to the next layer, where it's also having a function performed on it, and it's sending the result of that to the next layer. And it goes like that. There's big ones and there's smaller ones. I'm only doing a general overview of artificial intelligence for beginners, so I'm not going to get into the very detailed levels of this because I think that's outside the scope of this presentation. But yes. And here's an example of a deep learning neural network. So this is an image classifier where it's taking the image input, which is of George Washington, I think. I'm not sure, but I guess so because it says George. It's showing what each of the different layers are potentially doing. So the input layer here, it's telling us that it's identifying light, dark pixel values. And then it gets passed on to the next layer. Each neuron is passing its output to each neuron in the next layer. And then those are making calculations. They're performing a function on those inputs. Here it says identifying edges, and they're passing the outputs to each neuron in the next layer. And it goes so forth and so forth until you get to the final output layer, and then it's making a decision of which is the most accurate, which has received the highest score. And it's identifying the combination of features, and it's telling you the output. Yeah. What is AI capable of? So far, it's capable of quite a lot. Natural language processing, which is content extraction, classification, machine translation, question answering, and things like that. It's a lot of what we're doing at Bank of Georgia right now. It's very interesting. Speech recognition, which could probably be divided into two parts, which is speech to text, and then the opposite, text to speech. Then there's computer vision, which is both image recognition and machine vision. So identifying what is in an image, which kind of works by classifying different parts of the image. Movement, so self-driving cars, which there are examples of. It's very easy to follow examples of you getting a remote control car and attaching a camera to it, or even you can teach. There's online games, web-based games, where you can write your own code and using Google Colab and teach a car to follow the road and things. It's very interesting. And then playing games, which here in the corner, I think it's called Stick Cart or something. It's an example that's on the PyTorch website. It has good documentation. It's an example of reinforcement learning of the aim of the game is to hold the stick above the cart, and the cart's only able to move left or right. And using artificial intelligence, using reinforcement learning, that you're able to teach the cart how to make sure the pole stays above for the longest time. Yeah, I think that's the end of my presentation. I want to say thank you for this opportunity, and thanks for listening to me. If you guys have any questions, I'm here and I'm able to answer. After I know that after me comes Nikoloz, who's going to be talking. He's going to do a workshop on natural language processing, and then after him will be Makho, which will be doing a workshop on speech recognition.
Thank you, Karanam. Hello, everyone. It's my second time when I'm speaker on DataFest, and I'm very happy. It's really good experience. I know it's Friday, it's late, but I'll try to focus your attention once more because it's very, very interesting topic. I think Levan covered many sections of AI and fields, but in general, and I'll try to focus your attention on NLP. What is NLP and why it's important and interesting? NLP is natural language processing, and natural language processing is hard. Why it's hard? Because that shouldn't be hard because it's natural language, right? But it's hard because it's natural language for humans, and we want to do it with computers. And for computers, it's not natural language. Computers can't understand text; they only can understand digits. And because of that, compared to other traditional machine learning methods, we need to transform our text data to the specific form to do machine learning tasks on it. And I'm gonna do practical hands-on tutorial for this. I prepared the notebook on Google Colab. I'll try to share my screen. 1 second. I have two notebooks. One is already filled and one is empty, but we have this structure, and I want to share this link to you. I want you also to open this notebook. It's completely online. It's running on cloud. You don't need to install anything, so we'll do everything together. I hope if I copy this link, you will be able to view this document, and also you will be able to copy and run it on your drive. 1 second, let me put it in the chat. So I put the link in the chat, and you can take this notebook, copy, and follow me on this tutorial. So let's start with a few words. We're gonna do this data preparation for NLP and then do sentiment analysis. It was a question some minutes ago that how to do sentiment analysis, and I'm gonna give you this tutorial. So we have this structure of notebook, and I want you to also comment if you have any difficulties opening this notebook, because I think on tutorial it's really important you also to practice and write it yourself, or we can do together. So if you have any difficulties, you can write in the chat, and I'll try to help you. So we have this kind of table of content. We are gonna prepare our environment for natural language processing. Then we're gonna do tokenization and text cleaning. Then we're going to featureize our text with different forms, because it's a really important component of natural language processing pipeline. First is bag of word featureization, then TF-IDF, then word to vec. So it's from most basic to most advanced. So let's get started. If you open the Colab notebook, right in your browser, you can run this cell, and it's executed in the Google Drive on server. So first of all, we are running this command to install all the necessary libraries. It's Python libraries. I think many of you know these libraries, or most of them. So it will install that, and then we will import these libraries specifically. And then I prepared the snippet, the function which will load IMDb dataset. I think many of you know this dataset. It's about 50,000 reviews of IMDb movies, and we want to predict what kind of sentiment was in a specific comment, because this sentiment analysis is one part of natural language understanding with machines, right? It's quite basic, but quite challenging task. So I prepared this function. You can run it, and it will load the data in your memory, in your notebook's memory. And if it's not downloaded yet, it will download itself. But if it's already downloaded, it will use cached version. So then we're gonna sample some observations from this data, and we'll see how it looks like. I think many of you know Pandas library, and I have put this data into Pandas data frame, and it's 20 example of this data, 20 observation. You can see that there is text review as in the raw form. Then there's a flag if it's train set or test set. If it's 1, it's train set. If it's 0, it's test set. And is positive is binary also. It's flag. Is positive means that this comment was positive. It's a label of the review. So we're gonna predict this label if it's positive or not. So how are we going to do that? First of all, this text is not understandable for a machine, right? We need to featureize that to run the machine learning task. First of all, we need to tokenize this data, and for that we are using this kind of method. We have data in our data frame, and we are creating new column, and we transform our text column, and we transform in such a way that we are splitting the string with white spaces. So we get data tokens, new column, which is in the form of list, Python lists. So in each observation we have a list. And why it's important? Because we have the tokens. We say that each word is a token. There are different kinds of tokenization. Some modern ones are subword tokenization, byte pair tokenization, but we are using the basic one. Basic one is white space tokenization, and here it's the implementation of that, very, very basic. So we have tokens in the list, and now what? Now we want to remove the punctuation, right? Because punctuation is not important. It's not so important in sentiment analysis, because mostly people put incorrect punctuation marks in their sentences in the real world. So we get rid of that. So how do we do that? First of all, we define translation like this. We say that we want to remove punctuation from the string. It's a table which translates string into non-punctuation string. And here we use that table to change our tokens. How do we do that? Data tokens apply. It's a custom function, lambda function, as you know. W translate table for W and X. So we are translating each word in this tokens list. And let's see how it looks like, right? Takes a bit. Yeah. So there is no punctuation anymore in that. And now we need to strip accents, because here you see this is accent letter. We want to remove that accent and change to A, because it gives us more tokens, and more tokens are more classes, and more classes are hard for machine learning. So we'll try to strip that accents. And how do we do that? We use unit decode library, which we imported before, and we are using custom function again, unit decode. We use the list comprehension in Python for each list in the observations. So let's see what will happen. It takes a little bit of time. So this A is removed in this version, right? You see. So we already have more cleaner version of our tokens. Now it's left to normalize the case. We don't, we don't normalize the case, we know that Python is case sensitive. So this token, this, is not the same as this. Let's test it. This, it's false, right? Because of this, we want to lower the number of tokens, and we normalize the case. For this, we also use list comprehension with pandas, and we are doing like that. Lower, it's a string method. And, oh, sorry. It's case sensitive, as I said, and it should be uppercase S. Okay, I think it's done. And now let's see, let's check our data. Yes, this is lowercase. Everything is lowercase, and it's easier now to do our modeling on this corpus. So we have the tokens. Now the next step is to vectorize these tokens. What is vectorization? Vectorization is the same as featureization. In machine learning, we need features, right? And text is not features. So we need to encode this information, which is given in tokens, somehow to represent it as a feature, as features. And it's really, really hard task, because it was latest improvements was really great, and before that it was really hard. And I will cover different methods for that. The most basic method is bag of words, and bag of word means that we count each word in each document, and each document in our case is each row, because it's one comment, and we need to count each token, each unique token, and its frequency in this document. For example, how many times this is occurred in this document, and so on. And for that, we're gonna use a specific library, scikit-learn. First of all, let's split our data to train and test set, because we know that when you start machine learning, you need to split your data, otherwise you will have data leakage. Is train equal to 1, copy, and test data is equal to. So we are saying that when train is flag is 1, it's train. So we are saying that when train is different data. Flag is 1, it's train. So next one is to vectorize. So we have two different data, and we use so next one is to vectorize from our data, and we use pre-built class from scikit-learn, which we imported in the first count cell. It's a vectorizer. Let's call it vectorizer. Purpose of using count vectorizer. And for the purpose of memory issues, we are using these parameters. Imagine in each document we have crashing memory, and this because imagine in each unique document we have lots of words, and these words are if we take unique words in this 50,000 documents, there will be many unique words, and each word goes as column. And each document is row. So if it's too much columns, we can't vectorize it in memory. And so we are restricting that so that we only use the words which occur at least in 10% of documents and maximum 18% of documents. So it's relatively small, and we define our X as features with vectorizer, fit, transform, its popular form of scikit-learn, featureizers, train data, tokens, apply. So what we are doing here, we are doing very simple thing. So what we are doing here, we are doing very simple thing. We want to fit this vectorizer so that it counts each word in each review, and we are using that with white space tokens. So it works here, and we are concatenating it with white space. So it works on strings, and we use apply for that, and then which means these vectors are sparse, are in sparse representation, which means that scikit-learn gives us sparse representation because maybe you have many unique words and you cannot fit it into memory, and it gives in dictionary form, sparse form, and we want to explicitly change it to array because it's more intuitive form for us to work with it. And I'll show you how it looks like. Its shape is 25,000 rows because we have in train set 25,000 rows, and in test set also 25,000, and 205 columns. And each column here is number of word in first document, and for each column we have this count. So we're gonna use that. We are gonna use that X features for classification. How are we doing that? First of all, we're gonna define our model. Let's use linear classifier, logistic regression for sentiment analysis, because we have binary class, and it's very intuitive to use logistic regression. I think many of you know that. And it's scikit-learn class, and we're gonna indicate that it's SAG solver because we have big data frame, and this is stochastic gradient solver. Otherwise, we cannot fit it to our model. So model fit X train data is positive. So what we are doing here, we are going to train our model on X, which was defined here, and as a target we are using is positive label, which is in our data set. You remember here, is positive was 1 if it was positive and 0 if it was negative. So it's classical binary classification problem. So let's fit it, and we're gonna get the fitted model, and now we're gonna use it. Let's check the accuracy of the model, right? So first of all, we will use it for test set because model didn't see the test set, right? So let's measure the performance on that. We are transforming test set. Oh, sorry, we have already that. So we're gonna y hat is model predict X. So it's y hat. Sorry, 1 second. So we do it on test set, test data, and the same logic goes here. Oh, we have a typo here. Test date. So it takes some time. And we have our y hat, which is our predictions, and we here see that it's half. Sometimes it's 50% times it predicted as positive. and it looks like this, and we have the shape of 25,000, and we're gonna use classification report for illustrating the performance. And this is a scikit-learn class classification report. I think you know that. And first argument is true label. Yeah, that's it. We have this report of our classification. Our features worked, I think, because it's not random predictor. We have accuracy of 76. And the accuracy is really good metric here because we have balanced class, and we can say that our model is 76% accurate in terms of classifying our IMDb comments. But it's not enough, right? We often want more accuracy because it's basic model, it's bag of words. Now we want to change our approach and use TF-IDF. What is TF-IDF? People say that, we say that only number of occurrence of term in a document is not enough. We want to weight it somehow to be more representative for feature. I'm gonna show you what is TF-IDF and how it's used in machine learning. TF-IDF is a formula which shows that how many times each term is occurred in document multiplied by inverse document frequency. So how many times this term was occurred in all corpus documents. So if it's very specific for this document, if the word is very specific for this document, we score it by number of occurrence and also inverse number of occurrence in all documents. So how do we implement that? Sorry, I will answer your questions after this session because I will not have enough time. So let's answer in the end. So first of all, what we are doing is we are implementing vectorization using TF-IDF. So same logic here. Train data is equal to data when data is trained. Copy. Data same typo. So we have different vectorizer here. Vectorizer is equal to the TF-IDF vectorizer, and the same restrictions. The mean document frequency 5%, and max document frequency 80% because memory issues. And we're gonna use that vectorizer, fit, transform, train data, tokens, apply, join X. Let's see how it looks like. Yeah, it's parse array, and we're gonna change it to array. This is the shape. The same shape and the number of dimensions more. It's NumPy array, and in each column now we don't have integer, we don't have only number of occurrence, but we have an index which is logarithm of the ratio of term frequency and document frequency. So it's some float numbers which is more representative than just number of words. And now we're gonna use these vectors in model, and let's define the same model here to compare the results. Logistic regression, solver is equal to SAG, model fit, X, train data is positive values. Let's train our model. It's really fast. And now we're gonna measure the performance. Transform data. Okay, and y hat is equal to model of predict x. Let's see. Oh, sorry, here is a typo. Landios. We're gonna do this here. So we have the same shape, and let's see the predictions. It's 51% of positive class as predicted, and the same here. Print metrics classification report. Test data is positive values y hat. It's y hat and y true. We are doing in this form. Oh, it's more accurate, right? We have 83% of accuracy, and it's way better than before in bag of word case. And we say that it's really better representation of text in terms of in terms of vectors than bag of word representation. But we can do more. We can encode our data into more interpretable form. In this case, synonyms are not similar, and we know that in human language, in natural language, we have synonyms, and some words are more similar to each other than others, and it's not binary, right? So Google and Nikoloz introduced a new model a couple of years ago called Word2Vec, and Word2Vec is very, very famous and very interesting model. You can check it, more details on the web. It's everywhere, so it's very interesting, and it's dense type of representation of text in dense features. And there are pre-trained models of that, and we can use that. We don't need to train it on our corpus, so we will use already pre-trained model. We use downloader load globe wiki giga word. So it will download the word embeddings of Wikipedia corpus, and in this corpus we can see that there are lots of words, unique words. For example, vocab is equal to set word vectors vocab keys. So let's see how many words do we have in that corpus. It will download now. You can see now that it's quite big. Come on. I think it has some issues with downloading. So let's stop and download it again. I'll try to restart my runtime because we don't have very much time. So we're gonna skip the code before. We're just gonna run these commands. Tokenization. We don't want bag of words, TF-IDF. We want Word2Vec. So let's run these cells. And meanwhile, I'll tell you that this is really, really interesting model. It's neural nets, which is representing our raw form of text into dense vectors, and how it's doing that. It's very interesting itself, but it's not in our scope of this presentation. It is using skipgram and SIBO, which counts the co-occurrence of words in the same context, and it predict the similarity in that way. So let's download this corpus, which is already pre-trained for us, and it's pre-trained on very big corpus on Wikipedia corpus. I hope it will download. I think it's already loaded, so it's on that. It's stuck somehow. If it will not download, I'll try to use other model. Oh, I think it's downloaded. So let's say it's 400,000 words, unique words. And each word is a vector. Let's check it. Word vectors, man. It's a vector. It's 50 numbers, and each number is a float, -1 and 1, -2 and +2. It's normalized, and it's very representative. So what we can do with it is very interesting thing. We can use the analogies of word2vec. For example, we can use this method to see what's the relationship between king and between woman and queen. So if we do like this, woman, will give us queen. So it has, these vectors can represent the relationship between king and man, and it can predict what would be this kind of relationship with woman. Then the most probable is queen. Also, it's throne, prince. It's very intuitive, right? For human, it's very interpretable. And this model is really useful for that, but it's just intermediate step in which we can use that. But we want to use it in our classification as vectors. So the same here. Using this traditional method. So what we are doing here, we are gonna vectorize our data again, but with word2vec model. How it's done, we are going to index our word in this dictionary as we did for men, like this, word2vec men. If you put the string here, it will give you a vector, right? So for each string in our tokens, we are using word2vec indexing, and then we are, if it's in the vocab of word2vec, and we are vectorizing it with NumPy array. So let's see what we have. And then we're gonna put one more line. Zero. So what we are doing here, we have different vectors. For each word, we have vector in the document, and we need to average these vectors in order to represent the whole document. So we are doing this with NumPy, with mean averaging, but you can also sum. It will work differently. And there are different techniques for weighting these words in the document, but we will use this simple one. And now it looks like this. It's a NumPy array, and it's this form. As you guess, it's number of observations, it's number of dimensions for our documents. Now let's do classification for that. A model is equal to linear model, the same here, logistic regression. solver is equal to SAG, model fit vectors, train data is positive values as it's our target, and vectors is equal to test data tokens apply lambda x. Word vectors I for I. Same here for test data, and the same here for this line. Let's do that, and we're gonna use y hat for prediction, model predict vectors, just like that, and then print matrix. Sorry. Here. Oh, yeah, because there should be typo again. Online demos are always like that. So then we're gonna predict with this vector, and then use that for classification report. Classification report with test data is positive. Use y hat. Here we see lower accuracy with this model. Why it's like that? Because it's better model, it's more advanced model for word representation, but it's not good for whole document representation. We are just using mean pooling for the document, and if we would try to represent each word as a vector, the word to vec is much better than the previous ones, but for document classification it was less accurate. So it's like that, but it's more advanced model, trust me. So the next one is transformers. Transformers are the most advanced models nowadays, and it's a very big thing in natural language processing. Google again introduced BERT. It's bidirectional encoder representation from transformers, and it transforms each sentence to encoding, to embedding, and not each word like word to vec. So if we have each sentence as a vector, we can do machine learning pipeline on it directly. And it's really easy with the help of transformers. This is an amazing library, which is my favorite nowadays. It's really great. It uses TensorFlow or PyTorch as you want, whichever you want. And it has many pre-trained transformer models, and you can also train yourself on your custom corpus. So we're gonna use that transformers for illustration purpose. We're gonna use test data. Data is train is equal to 0. Copy. We have our test data. As you remember, it's just 25,000 comments, and we use classifier directly. It's not vectorization, it's directly classifier. We can use transformers for that. It's much easier. We have this pipeline imported before from transformers library, and we use sentiment analysis. And this is a task for which we want to use this pipeline. It can also do other tasks like summarization of text, and also translation, machine translation, and many other NLP tasks. So we have this classifier class. Now what we are doing is we are gonna create our variable x from test data tokens, apply lambda x. Join our tokens to the string. Then we're gonna trunk our sentences, because it cannot understand very big sentences because of memory issues, and we only consider sentences for which lengths are less than 1,000, and then sample number is equal to 100, place equals false, and random state to be reproducible equal to 42 as its answer to everything. So we have our X. We only take 100 examples from our data set because it's very GPU heavy model classifier. It's very big transformer and it needs GPU and not our Colab notebooks, which is very weak for that. And we only use 100 sentences to classify just to illustrate how it performs. So we need our target. Target is test data is positive log x index to list. So we are using the same indices which we used here. It's we filtered the data frame of features here, so we need to filter our target also like that. And we are using log method of data or of pandas data frame, and we have y data frame corresponding to the features, and this is the label. Now what we're gonna do is y hat is equal to empty list for I in range x shape 0. We use for loop y hat classifier, and we're gonna use classifier directly on our raw form of text. It does everything itself. This method, this is the classifier callable, which can directly transform the raw text into the prediction, and we save it to our empty list. Let's do that, and it will take some time because the classifier is really heavy method for CPU. But if you have, for example, RTX 3090 at your home, you can use it very well, and it's really fast on GPU. And now y hat is list, so we're gonna do array from that, and array is hard because it's not traditional form. In y hat we have this form. The prediction of transformer is like that. For each observation we have list of label classes, we have label negative, and the score of confidence is 90% 0.94. So we take this 0 element, I mean in every list there is 0 because it works on batches, and we have one batch, one observation in each batch, and we're gonna take the first element from this batch each time, and then we take the label key and the value of the prediction, and we don't care about score. So I'm gonna write this logic for you. Label is equal to positive multiplied by 1 because it's Boolean for I in y hat. So let's see how it looks like. It looks like our predictions before. It's 0 if it's negative and 1 if it's positive, but it's our predicted class. So our final line of code, and I am finished. Metrics classification report y hat and y. Let's see how it performed. It performed with 87% of accuracy, and it's just these lines of code, and it's pre-trained version of sentiment analysis, and it works with 87% of accuracy. But it's quite slow, but you can tune this model for your specific tasks. You can use pre-trained one, or you can train your transformer, and it will perform much better. It's really good for sentiment analysis and other NLP tasks. I wanted to cover these things with you. We covered some methods of vectorization and one end-to-end pipeline, which is given in Transformers library, which offers you just everything ready and you can use it for NLP. So I hope I'm not very late, and I will give tribune to Makho. If you have questions, I think it would be better if we answer after the session when Makho ends his presentation. So Makho, please.
Do you hear my voice? Unfortunately, my video camera is out of tune, as always. So you have to pardon me for for that part. But other than that, I'll try to deliver what I want to say. So firstly, before we start the actual implementation, I just want to call out that the current session is intended for beginners, and this will simply be a superficial and rather short interview of audio processing and speech recognition. Recently, in Bank of Georgia, we've been working on developing speech recognition technology and more specifically, production quality audio processing pipeline. Okay, I'll continue. In a nutshell, what I wanted to say that in a nutshell, we wanted to compete with Google's speech to text, as we were not satisfied by its accuracy on a domain-specific data. For that reason, we started to research current state-of-the-art models, which could leverage the fact that Georgian really struggles with labeled data. And actually, we came across Wave2Vec. Maybe many of you have already heard of it or even used it, but I'll still go with a brief description. Wave2Vec is a convolutional neural network, shortly CNN, as you all know, that takes raw audio as input and computes a general representation that can be further input to any speech recognition system. It actually acts like an audio featurizer, like, for instance, MEL spectrogram, which is still heavily used today to vectorize audio and transform them into training data. The main essence in Wave2Vec training process is that it is trained contrastively as it tries to distinguish samples of 25 milliseconds from its distractors, thus trying to learn general characteristics of natural speech. Other than that, I won't go in any further detail. So let's start with implementing the whole pipeline from start to end. I'll share the link that you can follow, or you can at least watch my screen. Okay. No, okay. So. As you can see, the pipeline mainly consists of two parts, first of which is audio pre-processing and collation, and the other part is fine-tuning. So let's go step by step. For demonstrational purposes, the code was simplified for today's use case, so don't take it for granted. For the data, we'll be using Common Voice Open Georgian Speech Corpus that contains only 3 hours of labeled speech. And okay, let's just unveil the codes. So this part is responsible for pulling the corpus, but yet again, for demonstrational purposes, let's constrict the data sets by taking only 5% from each of them. That way, we can just quickly demonstrate the transformations that could otherwise take like at least hours. Okay, so I'll just rerun the code so I'm certain that it works. Let's keep this part. It's just a function that is responsible for picking some random elements and printing them for demonstrational purposes. Now, here the main part of this pre-processing part, kind of. Here we have a regex code that is responsible for picking all the symbols, all the letters from the Georgian alphabet, and plus white space, so that the model would know about all, so that the model would work only for those letters and nothing else. Okay, so let's try to run it. And yet again, here we can see some random sentences, and we are sure that no symbols other than Georgian alphabet and white space is present in those sentences. At least I'm pretty sure of it. Okay, the next step is processor initialization. Processor is just an object that unifies tokenizer and extractor classes. First of all, let's extract all the cars that happen to be in our data set. But always be aware that sometimes if the data set is too small, you could be missing some of the letters from the alphabet, which happens to be the case for this one. And I'll show that in a mere seconds. And let's print the extracted symbols. And here we see that only 33 symbols are present. Only 33 letters from Georgian alphabet, 32 letters from Georgian alphabet with the inclusion of white space. So in this case, you would have to manually set the vocabulary, because our data set is way too small and it doesn't contain all the letters. But that won't hinder us from continuing. Let's add some special tokens which are used for the model to function correctly. For instance, end token, which you can see right here, it is presented as an S symbol /S. It's an end token, which is responsible for padding at the end of every sentence. And during the decoding, it acts like a breakpoint. Then there's also a pad token. That is literally used for padding sequences of varying lengths to some constant. And lastly, we can see here unknown token. This part is not used in our model, so we can just omit it. And as you can see, our white space symbol was just renamed as a vertical sign, just for a visualization and nothing else. And the last one is S symbol. If anyone's interested, it is a start token, and like end token, it is used for denoting the start of the sequence. Let's save the vocab file, and here we can see that it was really saved. I'll just go out, content. And here we have our vocab JSON, which is yet again just Unicode symbols. Sorry for that, but Colab doesn't show us normal strings. Now we have to instantiate two main classes of transformers for wave to vec, which are responsible for instantiating our processor class. The very first one is tokenizer, which is instantiated by using our vocab JSON and our special tokens, and then it just tokenizes, like Nico showed, every sample. And the next one is feature extractor. What's special about feature extractor is that the main parameter it uses is a sampling rate of 16,000. And in our case, that's because Facebook's FairSec team used the model. Well, the Facebook's FairSec team used the model to model speech to text on 16,000 kilohertz data. And as you know, because speech is continuous signal, it needs to be discretized. And that's why we use sampling. And that's what is called sampling. Other than that, the basic part of audio preprocessing involves upsampling or downsampling, because usually audio data is not present in 16,000 kilohertz. So we have to somehow downsample or upsample it by any means. And in this case, we'll be using Librosa, which is a really fine audio library for that purpose. You could also use any other library, even Torch Audio, which I'm using for loading audio vectors. Okay, let's just run it. So in this code, we are just loading our audio in some dataset format, which is the main, which will convert to the dataset that will be used for day calculator. But now we have to resample our audio to 16,000 because the audios in open Open Common Voice Corpus are present in 48,000 kilohertz. That's why we have to use Librosa to downsample it to 16,000 and then use augmentation techniques. And here comes the non-basic part of audio processing. As you all know, pre-recorded audios for modeling contain little to no noise. But that's not the case for real-life audio recordings, where background noise runs really rampant. Therefore, we have to somehow distort our perfect recordings to somehow simulate the real-world settings. Neglecting this very fact usually translates to pure model performance. Audio augmentations is a really great library for that purpose. And as you can see, the augmentator consists of different kinds of transformations. For instance, like adding Gaussian noise, time stretching, pitch shifting, or just shifting. And in this case, I just used the probability part of 0.0 because I just don't want to heavily use it in our example. But other than these transformations, you could just use any other noise like white noise or Gaussian white noise or even background noise. And what I mean by background noise is the fact that you could use any background audio that could simulate natural noise or even silence. And in this part, okay, path, okay. Dev speech path. Maybe I just skipped over some speech. There seems some kind of path problem. Error path. Maybe I just skipped over some kind of. I'll just run it again. Then sample rate. Then. I don't really know the reason why it does not run, but the key error pass means that I don't have the pass keyword in my dict. For instance, okay. That happened because I reran the same code and I already got rid of column names of my common voice train. That's why it happened. I was careless. So here is the actual transformation happening, which the first one is free sampling and the other one is augmentation. But the augmentation part is kind of not mandatory in this example because we are not using it at a great degree. The next part will be just making sure that all our inputs have the same sampling rate of 16,000 kilohertz, and then just removing the, not removing, but just renaming the columns. Like for instance, we are just creating labels column. That means the actual text for an audio. Okay, let's make sure that everything's okay. Okay, seems that everything is okay. So the next part is instantiating of data collator, which is just a Hugging Face data collator object. And I'll just go with it and instantiate in a mere seconds. And here comes the real instantiating part. And now for the modeling part. So as a metric accuracy, we'll be using word error rate, which I think is the most relevant assessment of model performance. It actually just computes the correct words in the whole sentence. Okay. Next, let's load the pre-trained model in our XLSR. Okay, so our runtime was shut down. It happens with Colab all the time. So I'll just rerun the whole code yet again. And till it loads, I want to say that we'll be using an XLSR 53 model, which was trained by the Facebook's FairSec team on a multilingual audio corpus. Audio augmentation, okay. And then data collector. hopefully it will run this time so that we don't have to rerun the same code again. Or otherwise, I'll just go straight to the demo part. So either way, let's just continue with the code. So what happens next? After loading, our metric, we are just dropping it for the use in our trainer. And after that comes the actual, okay, everything seems to be okay. And for this part, let's just get Facebook's FairSex large XLSR 53 model, which is the base model of wave-to-vec. And as I mentioned already, it just represents an unsupervised model, which was just trained on a large audio corpus. And what we're trying now is just loading the base model and building a CTC layer on top of it so that we can train it for a downstream task, which is in our case, speech to text. It yet again could be used even for text to speech or any other text audio processing, audio processing pipeline. Okay. Now we are just freezing the base model, the layers of the base model, because it takes like transfer learning, because the base model just transfers all the base knowledge to the CTC layer. So so that it simplifies the training process and learning part. Now, let's run this one. This is the very last step, almost the very last step of our model building parts. As we see, we are just loading training arguments and hyperparameters of these training arguments is just out of the scope of today's session, but I just want to say that all the hyperparameters are self-explanatory. For instance, we are just using eval loss for loss monitoring, and so the model knows that it should only look for evaluation loss, and if it does not decrease, then the model isn't learning. So that we could early stop the model, which can be edited like this. If you can see, we are just loading from transformers early stopping callback, which acts like a breakpoint, as I already said, which stops the model if the learning process does not progress further, which means that evaluation loss is not decreasing. And lastly, we will be initializing trainer, which just unites all of the objects that we initialize this far, and then we are ready to train. But I want to say that this model, this XLSR model, or even any large or small wave-to-wake models, are really dependent on hyperparameters. It is so sensitive to the hyperparameters that in one case you could just see the performance of, for instance, 50% word error rate, and in other case like 100% word error rate, which means that model has learned nothing at all. which is kind of catastrophic. But that's why you have to just go and do some research before starting training. And if you want to, if you want to have a great, a good source for instance, for a good starting point, you could just check out Hugging Face official website, and there are already some Georgian speech-to-text models, and you can just copy those training arguments and use it in your transformer. Use it for your model. And yet again, it's a transformer as well. And I would recommend that you would just use the already tested settings for your models, which I already mentioned are present on Hugging Face and even on Fair Sex Facebook. If you are just training for a bigger hours of data. Okay, and the last part is to just run the model, but this will take way too long, and let's just skip this part. But I'll just run it for the sake that it works and it does not crash. Okay, I'll just stop it there. Okay. And for the demo part, I just decided to just load the model that we trained in our research lab lately, and it was trained on a 10-hour long data set, which is not that much, and it was trained without any audio augmentation techniques, which I mentioned earlier, like adding some noise or just slowing down audios or speeding up the speech or just changing totally the pitch or loudness. I'll just run the code. So this part is responsible for loading our own checkpoints. Okay, so there is no Google Drive present here because our no. Okay. Okay. Always works on its third time. Perfect. Now let's load back our model. Okay. It will take some time for the model to unpack because it's like 4 GB in size. but till it loads, I would just mention this hyperparameter FP16, which stands for half precision floating point. And by activating it, the deep neural network will use 16-bit floating point numbers for weight representation other than 32 bits. And that actually just fastens the training parts like 2 times or even 3 times. But you have to have like CUDA support for that. If you are training it on a CPU, that's not an option. Okay, we can see that our model is unpacking. Okay, so the model unpacked. Let's just load it. So we are loading, as you can see, processor, which incorporates tokenizer and feature extractor in itself. And the second one is our model itself, which we loaded from our own checkpoint. Now, this part is responsible for audio recording in Google Colab, so we can just skip it. It's not that difficult. And let's initialize our predict voice, and let's try to just test it out. გამარჯობა database-დან. As well, sorry, this was just an example, and because this was just trained on a Georgian language, that's why it was obliged to speak in Georgian. And other than that, we could just try any other word. Let's try another one, but the model's performance is not that great at this point because in reality, it could be no more than or no less than 60% word error rate, which is not that great. It really lacks in detecting fast speech, and that's why it's I'd say it's totally unusable at this point. Well, at this stage, but there's some ways to actually make it better, like the decoding process, which I haven't talked about. At this point, we are just decoding it like this. We are just predicting in each time interval, for instance, in every 25 milliseconds, which character was present in an actual audio. And if there's nothing present, then the model would just predict with the highest probability the blank token, or sometimes it would predict padding token or delimiter token or white space, in other words. And that way, we would just construct a probability matrix with all the vocabulary letters and with its respective probabilities. And if we chose all the highest probabilities, we would just go the greedy way. That's why it's called greedy decoding. And that is the way that is used here. So in a way, we could say that greedy decoding is just the pure model performance and nothing else. But there are other just smart ways of decoding, which incorporates like language models in it, because we could just use some kind of outer knowledge which model was not exposed to, and we can just alleviate some problems that greedy decoding has. But at this point, using some other kinds of decodings is really out of scope, but I would recommend you to look into the beam search decoder. What's great about beam search decoder is that it just picks different hypotheses and just tries to lean out the bad ones, and so that the our decision process is left with only one more plausible hypothesis, which is in our case just the sentence, right, which was decoded. And if you want to see how the padding process happens, so the tokenization process happens, here it is. As we see, the model started with predicting the pad tokens in those 25 millisecond time intervals, and we see that it is way too much. And after a certain point, it's just printed G, then again pad token, then again A, and A. And so the decoding process goes like this. If we see two consecutive sign letters, we're just uniting it so that we are left with one. But if there is like double letters in a word or in an audio, that way it would just print A, then delimiter symbol, and then again A. So we would know that there's like double A's in our case. And so let's just see that kind of example. ნამდვილად არ მეგონა თუ ასეთი კარგი მოდელი გამოვიდოდა. Sorry. ნამდვილად არ მეგონა თუ ასეთი კარგი მოდელი გამოვიდოდა. Okay, so the model was mostly correct, but it just did some segmentational error. That would be way too easy to correct. And let's see the padding process. Okay, so Gamo, okay. Well, this is where there should be some, there should be a delimiter symbol, because that way we wouldn't know how to get rid of those double A's. Well, but maybe I'm not really sure of the rule of how the later calling happens. So that was all I wanted to show at this point. Hopefully you have the presentation. Okay.